Right, so let's go over how an object reaches terminal velocity. Specifically, we're going to look at a skydiver jumping out of an aeroplane. So initially, then, let's start with step one. So initially, the skydiver has just left the aeroplane. We know that the skydiver is going to experience a large force of weight right here. So because the skydiver is experiencing a large force of weight, he will accelerate. Okay, so firstly, he jumps out of the plane. Initially, he starts accelerating. And he accelerates because there is a large resultant force downwards. Okay, now there is a large resultant force downwards. You know from Newton's first law and Newton's second law that a large resultant force is going to mean a large acceleration. Now, as he gets faster in step 2, so as he starts building up speed, the force of air resistance is going to increase. Yeah, he's falling through the air faster, so air resistance will go up, or drag. The force of drag will go up. So the weight is going to stay the same. However, air resistance is going to start to grow. It's going to start to get bigger. So I'm going to call that drag. So drag starts to get bigger. Okay, now, so as his velocity increases, his drag does as well. Now, because his drag is increasing, his resultant force, the resultant force he experiences, will also decrease. So what's going to happen then if his resultant force decreases? Well, lower resultant force means a smaller acceleration. So he's still going to be accelerating. He's just not going to be accelerating quite as much. Right then, let's go for step 3. So a little while later, that force of drag will have grown to the point where it is equivalent to his force of weight. Okay, so weight and then drag is gonna be the same size as it. Okay, so at that point there is no resultant force. And remember, Isaac Newton said in his first law, no resultant force, the velocity will not change. So he'll stay at whatever velocity he's moving at. Okay. Okay, so there's no acceleration. So he's now reached what we call a constant speed, or a constant velocity. Okay, what would we call that constant velocity? Well, we call it its terminal velocity, so the object's terminal velocity. Okay, so he's reached a terminal velocity. Okay, now if he continued to fall, then he would probably die, because he wouldn't actually... He'll hit the ground very fast. So terminal velocity is something like 120 miles per hour for a human. So he's going to hit the ground at 120 miles an hour, and he won't survive, probably. So he needs to open up his parachute. So how does a parachute change his resultant force? So if we go for a fourth step here, he opens his parachute. Okay, so if he opens his parachute, now his force of weight isn't going to change. Okay, so his force of weight is still going to be downwards, but because he's opened his parachute, he has significantly increased the area at which the air resistance or the drag is going to act over. Okay, so he's significantly increased drag, so we're going to get a huge force of drag here. Okay, now because we've got a large drag, we're also going to get a large resultant force. But this time the resultant force will be upwards. Okay, so because there's a really big resultant force upwards, he is now going to experience acceleration in the opposite direction to his motion. In other words, he's going to slow down. So he's going to slow down rapidly. Okay, so he's going to slow down, he's going to decelerate. Okay, so he opens his parachute, he significantly increases the surface area, and doing so, he's going to increase the drag. So when you open up a parachute, there's going to be a much bigger drag for whatever speed he's moving at. Now, at this point, he's going to start slowing down. So stage 5, we know that as he slows down, the force of drag is also going to reduce. Yeah, so as he starts falling slower, drag will decrease. Okay, now drag will actually decrease to the point where it now becomes exactly the same size as his weight again. Okay, so to the point when it becomes the same size as his weight, he's reached a new lower terminal velocity. Okay, so he's going to open his parachute, significantly increase his surface area, Large resultant force upwards is going to cause him to slow down. As he slows down, the force of drag will go down until eventually it equals his weight again. And he's going to reach a new constant speed, a new terminal velocity at a much lower velocity than he was initially, okay, because that parachute is going to give him a much bigger drag for whatever speed he's moving at, and that's because he's got a bigger surface area. Now, if we were to plot this as into a velocity time graph, then we would see something like this. You'd see initially. So let's plot it for just before he opens his parachute. So if he just leaves the plane, he's going to experience a very, very, very large acceleration. Okay, a large acceleration on a velocity time graph is going to be a steep line. Now, as he starts to speed up, his force of drag is going to increase, which is going to slow his acceleration down, reduce his acceleration, until eventually drag and weight equal the same thing, and then that's it, moving at his constant terminal velocity there. Okay, and we can actually put a dashed line across here, and then that is our terminal velocity line. Okay, right. So that's it plotted into a velocity time graph. Now, I will see you in the next video.